So once again, welcome everyone. Today's speaker is Mr. Kusharasi. He is a doctoral research assistant in structural engineering, and he received his bachelor's degree from the famous Sharif University of Technology and his master's from the University of Birmingham, both in structural engineering. He's now a doctoral student in the structural engineering research group at the Department of Civil and Environmental Engineering at UMass Law. His research interests in ground penetration radar and signal processing, concrete and numerical simulations. The topic of his talk is the application of dual frequency ground penetration radar for subsurface void detection in culverts. Without further ado, Kusha, you have the floor.
Hello, everyone. Welcome to this seminar. So let's get started. Professor, I'm not allowed to share my screen.
Can you try it again?
Okay. Again, hello, everyone. Today, I'll be presenting to you our latest experiments on applications of dual frequency ground penetrating radar for subsurface void detection in culverts. Now, first, we're going to talk about why we're conducting these experiments and what the hazards associated with it in the introduction part. And then we're going to talk about motivation, the problems, and why we're using GPR out of all the other methods available. Then we're going to talk about the principles of GPR and how it works and the common obstacles associated with it. And then experimental setup, image interpretation, and of course, the final findings and results. Now, as you can see in the pie chart here, 20% of all the roads in the United States are in poor condition. And by 2040, we're going to reach a $3.36 trillion in investment gap compared to other developing countries. And as you can see here, the general expenditure in 2019 shows that state and highway expenditure ranks 5th in the total budget, which is a very, very high number. And of course, 31% of all the roads in the Massachusetts Commonwealth are in poor condition. And of course, these roads, these aging roadways and infrastructure cost an average driver up to $556 per year in repairs, and in some states nearly 1,000. Now, the problems that we have to deal with here, one is that the subsurface voids in pavements are a major problem in civil infrastructure because these defects are unnoticeable in pavement appearance in the early stages. These voids can lead to soil erosion and settlement, and the loss of subsurface soil homogeneity leads to capillaries that draw moisture inside the forming voids that will weaken the subgrade medium. And as you can see here, disaster will happen if not mended at late stage, causing sinkholes and potholes. Now, why are we using GPR or ground penetrating radar? Non-destructive testing and evaluation techniques, or NDTE, can defect this subsurface damage in early stages before catastrophic damage can occur. And GPR is very reliable, accepted throughout the civil engineering community, and it's very cost efficient and fast. And minimal technical training is actually required for doing field tests. And the abundance of manuals, journal papers, guides, and handbooks allow us to accurately interpret the images, such as the GSSI company's own handbooks and guides. And they are much less prone to noise and interference because of the low distance between the radar and the surface. And of course, the radar itself has some shielding. And the device used in this experiment is a UtilityScan DF seen here, controlled by a tablet, which is called the ToughPad. And this is actually an experiment in the town of Townsend, which the results will be published in the upcoming month. Now, how it works. GPR works by sending electromagnetic waves, transmitting downwards into the ground, And the amplitudes and arrival times of these pulses are related to the dielectric constant of materials, which range from 1, which is air, to 81, which is water, and are considered infinite for metallic objects such as rebars and steel culverts in this experiment. And they are depicted as hyperbolas, which we will get to that. And in practical civil engineering applications, magnetic properties are neglected and unimportant. Why? Because the material that we work with here are considered to be, which are non-magnetic. Depending on the dielectric contrast between the materials, part of the energy is reflected and part is absorbed across the layer interfaces. And the intensity of these reflections that come back is proportional to the dielectric difference between the two materials. And the brighter the reflection, the stronger the contrast. And as you can see here, the first signal is frequently referred to as direct coupling, which shows the location of the surface. And this is called an A scan. Now, an A scan is collected by a single transceiver antenna in a fixed position. And B scan is made up of a finite number of A scan measured at regular intervals along an axis. This is a B scan, and this is an A scan. And the C scan is a three-dimensional image created by merging simultaneous B scans on an XY plane with predetermined spaces. In this experiment, we're working with B scans. The common obstacles that are associated with GPR. One is that the EM waves are very much prone to noise and interference because every electronic device around us, cell towers, our cell phones, everything else they emit electromagnetic waves and they can interfere with the device. And image interpretation requires a lot of knowledge and experience in this field. And signal attenuation or weakening increases as the depth increases. And of course, another thing that causes signal attenuation is going in contact with metals and water or moisture. Another problem, which is actually very important, is that higher frequency equals more resolution with shorter length waves, but less penetration and vice versa. And the device which we use in this experiment, the GSSI UtilityScan DF, only allows one dielectric constant as input, which is not realistic. You can see a cell phone noise here. And as I said in the last slides, this is a metal pipe shown as a hyperbola with a strong, bright reflection. And another problem, as I said, that requires a lot of experience and knowledge to interpret the data is because sometimes you can mistake utilities like wire rings and PVC pipes and mistake them for anomalies and voids. The experimental setup, a 48 by 44 by 55 inches high roadway, artificial roadway section was built in the mechanical engineering lab by Mr. Nathan Kulkami and his supervisor, Professor Sabato. And a 30-inch diameter artificial steel culvert with a 30 by 3-inch hole was implemented in the middle section. And for this experiment, part of the soil was removed in 3 stages through the culvert defect here within 14 and 7 days of each other respectively. The device used here uses dual frequency of 300 and 800 megahertz. And as I said before, there's only one input for dielectric constant, which we set it to 6 for more accuracy, because you can see here, most of the materials that we work with in the subgrade are very close to 6. That allows for minimal dielectric contrast. So 3 called A, B, and C B scans were taken at 11, 22, and 32 inches in the X direction, perpendicular to the culvert for each soil removal stage. You can see the culvert here. And the scan 22 fairly passes the culvert's defect here. And this is the imaginative erosion pattern shown here. Now, for the parts of image processing, first, the B scans were important from the device, the ToughPad, to the Radon 7 software, which is a commercial software developed by GSSI itself. And the frequencies were split and saved as comma-separated values. And these files were important to MATLAB for further image generation and processing. And at the first stage, it was concluded that the 300 megahertz images were actually discarded due to lack of enough sensitivity to capture the soil erosion. And 800 is pretty good because the depths that we're working here are not very deep and allow us to use higher frequency for better sensitivity. This is the raw image. You can see the culvert here. One technique that was used was background removal. Another was contrast enhancement, which gave us a grayscale image. And it was also transformed to a field contour image for further interpretation. Now, the first scan line was scanned 11A to C. Now, 11A was taken right after the first soil removal. You can see that although we had a stage of soil removal, but we can't see a lot of erosion here, very, very weak hyperbole here. But as you can see in these two images, the section is fairly intact and can see the culvert clearly around 20 inches. For scan 11B, which was taken 14 days after the first scan, right after the second soil removal, and you can see the initiation of erosion is clearly visible here and here and here, as you can see, also depicted by the contour image. Now for scan 11C, which is taken after the third soil removal, 7 days after the second soil removal, and you can see here that the contour image illustrates the pattern of erosion going downwards through the culvert defect here, and there are voids forming here which show loss of porosity, and the soil is going downwards here. And what we see here is actually some loss of data. A small portion of the data was lost in this section for several microseconds, but that doesn't matter because we can see what we're looking for here. We can see the voids, the negative reflection depicted as black. Now, these are A scans taken at 25, 32, and 45 inches cross range. We can see the high scattering and fluctuations here for 11B particularly, and for 11C and 11C at 12 to 14 inches, which show loss of homogeneity. Now, for scans 22A to 22C, 22A, of course, again, taken after the first soil removal, but because it is actually right above the culvert defect where the soil iterations happened, the soil removals happened. So even in the first iteration, you can see the voids forming here and the pattern of erosion going downwards, and the culvert is not very visible due to high attenuation because of the accumulation of soil downwards here. Here is the asphalt layer, which is almost detaching from where it joins the soil layer. Again, we can see the coupling, direct coupling effect we talked about before. And in the scan 22B, we can see after the second soil removal that the dark regions are clearly visible, especially in the grayscale image, and confirmed by the contour image. We have a very, very negative shown in dark blue void forming here, another early stage void, which is indicative of high porosity. Now, scan 22C also shows advancement of the soil erosion. As you can see, compared to the last image, we have more voids forming here, and also the culvert is not very visible. We also have a little bit of loss of data here again, which is not important because we can see the patterns clearly here. This is the last stage. And you can see a very, very large void here, which is completely black, which shows there's almost no soil here, and there's a big void, an oval-shaped void. Now again, confirming the erosion with A scan cuts at 22.5, 32, and 45 inches. We can see that there is high attenuation here. There's high scattering here for 22B and 22C here. And at 45 inches, we can see that the signals are very well overlapping, and actually there is not much erosion happening at this cross range. Now, for the last iteration, scan 32A, after the first soil removal, we can see that the culvert is still fairly intact, like the image of 11A. Even though we had one soil removal, there is not much we can see here, and the culvert is fairly intact. But here we have some noise, which actually some data was lost. And for 32B, after the second soil removal, we can see that the soil erosion is visible, and the contour image indicates the migration of soil particles downwards, also clearly visible by here and here and here. And in this picture, in this grayscale high contrast image, we can see that the voids are forming around 6 inches deep. Now, for the last photo, we can see that the asphalt detachment causes a void and is visible at 6 inches, and the downward erosion pattern is clearly visible despite some loss of data here. And we can see that there is accumulation of soil downwards through the culvert hole. Again, these values of cross ranges, these A-scan cuts show that for this particular cross range cut, we can see that there is very small scattering here, also small scattering here, but a little more scattering for 32C at the cross range of 45 inches. Now, it was concluded from the experiment, as said before, that the 800 megahertz frequency actually produces much higher resolutions that can better capture and detect the subsurface void and soil erosion patterns. And the 300 is not accurate enough for this experiment. The soil erosion pattern depends on various factors like cohesion, friction angle, and therefore it is unpredictable. And this was an experiment in the lab with controlled environment. It's going to be much harder in an actual roadway. And GPR is again proven a reliable apparatus in this experiment for subsurface void detection and identifying soil erosion patterns. And of course, as you saw, the prior knowledge and expertise is required for accurate image processing and interpretation. And thanks to mechanical engineering doctoral students, Mr. Nathan Kulkarni and his supervisor, we could actually conduct the experiment on the artificial roadway that they built in their lab. Thank you for listening. Any questions?
Thank you, Kusha. But the first quick correction is on, actually, I think he's here. The doctoral student is Nitin. It's not Nathan.
Okay, sorry.
Okay, thank you for this efficient and focused technical presentation. Do we have any questions from the audience?
Nope.
Very important research, because we know the issue with potholes, what it would do to cars and other things. When you were talking about subsurface void, what is the depth limit? How far deep you go, that what is the limitation on that to get accurate reading?
Mm-hmm.
Thank you for your question. Actually, for the 300 megahertz, the depth in the device is actually shown to go up to 12 feet. And for 800, it goes up to 6 feet. But of course, there are a lot of factors that cause high signal attenuation and weakening, which these numbers are not actually very realistic. They're close to reality, but depending on what we want to capture, how precise it is, they may actually be lower. But that is actually what the device shows: 6 feet and 12 feet for 800 and 300 respectively.
Very good. Thank you.
Thank you.
Kusha, I have a quick question.
Okay.
And if you were provided with another opportunity to repeat the experiment, what would you do differently next time?
Actually, next time, I would try to put several voids, and not only in the culvert, but I'll make some defects in the soil itself. And of course, I would like to study the effect of moisture forming in the voids, because in this experiment, we didn't have any moisture. And I'd like to, because the New England area is mostly wet, and I would talk about moisture. I would try to experiment with moisture.
Mm-hmm. Thank you.
Thank you, Professor.
Do we have other questions from the audience? Okay, all right. Once again, thank you, Kusha, for delivering this short but focused technical presentation.
Thank you for listening. Thank you for this opportunity, Professor.
Thank you all, and we will have the next meeting likely to be scheduled next week. Thank you all.
Thank you all.
Goodbye.
Thank you.
Thanks, everyone. Bye.